Chapter 4, Part 2, we're going to be looking at conformational analysis. Combustion is a reaction in which a substance is combined with oxygen and produces water and carbon dioxide, if the substance contains carbon and hydrogen to begin with. And in complete combustion, it would completely form water and carbon dioxide. If the reaction does not go to completion, you may have incomplete combustion, where again the fuel that has carbons and hydrogens would react with oxygen to form water and carbon monoxide. Heat of combustion data can be utilized to determine or compare the relative stabilities of constitutional isomers. So if we were to compare the heats of combustion for 3 molecules that contain 8 carbons or have the formula C8H18, and we were to react it with oxygen to form carbon dioxide and water. And if you were to go through balancing the equation, it would take 12.5 oxygens to form 8 carbon dioxides and 9 waters. And so we could look at different ones. We could look at N-octane, which has the formula C8H18, or we could look at 2,5-dimethylhexane, which also has the formula C8H18, or we could look at 2,2,3,tetrabutane, which also has the formula C8H18. And we could measure the amount of heat given off, because when this combustion reaction occurs, it does actually release heat. So the enthalpy of reaction is negative. And what we observe is that N-octane releases negative 5,470 kilojoules per mole. The hexane derivative is 10 kilojoules per mole less, and the butane is even less still. And so the products in each case are the same. So they are the same products, which means they are the same energy. And the products are lower than the reactants because heat is given off. So in an exothermic reaction, the reactants are higher in energy than the products. And that difference in the energy is what's given off as heat. And we can see then that the octane is even higher in energy than the other 2 isomers because it released more energy. And if this is higher in energy, recall that that means it is less stable. And so what we could conclude with this is that the more branched an alkane is, the more stable it will be. So for the next part of this chapter, we are going to look at conformers and conformational analysis. And a conformer is simply a representation of a molecule in which you have a difference in a rotation around a sigma bond. So it's going to be rotation about a sigma bond, which of course remember that that is basically a single bond, and how that might look in space as it rotates around that single bond. There's ways that we can represent alkanes. So if we start with ethane, we could represent it, remember, with these wedge and dashes or the 3-dimensional, recalling of course that the solid wedge is coming out of the page. The dashed wedge is going behind, and a solid line is in the plane. You could also use things like a sawhorse, and it's often called a sawhorse because in one of the other conformations of an alkane, if we do it as like this, it almost looks like a sawhorse from a workshop, somebody's workshop. And finally, Newman projections, which is what we're going to be spending our time now talking about, are these Newman projections. And the bottom part of the Newman projection, the bottom image, shows what we're looking at. You're looking at the front carbon, and so this is as if we had this sawhorse and your eyeball was kind of here and you were looking down this bond. And so you would notice on the front carbon, you have a hydrogen up, which would be here. You have a hydrogen, whoops, I thought I changed color. You have a hydrogen here, which would be to your left, and then a hydrogen to your right here. And this, is that part that you just looked at. The back bond you're not seeing, so this purple bond here we're actually not seeing. And then this circle is representing what is attached to the back carbon and how does it look. So again, you would have this hydrogen being represented there, this hydrogen here, and this hydrogen here. So hopefully that will help you kind of understand what these Newman projections are showing. This slide again just goes over and tries to help you see that you're looking down a carbon-carbon single bond axis, and that you're looking at what the front and the back carbons look like. So let's go ahead and draw a Newman projection for the following molecule. And when you're given these instructions, you typically also need to know kind of what bond are you looking down. So I'm going to specify for the example of doing this problem, let's do this looking down the carbon-2, carbon-3 bond. And if you were to go back and name this from the previous lesson, we'd be looking at 2-chlorobutane, and we're going to be looking down carbon-2 to carbon-3. So this is carbon-1, carbon-2, 3, 4. And so our I, in a sense, is here looking down at the molecule. So therefore then, what I'm going to do is my front carbon is going to have a solid wedge with a hydrogen, and of course this dashed wedge is actually a methyl, and it has a chlorine. And so the chlorine's going to be up, and then if I were sort of looking at this, the hydrogen would be on my left and the methyl would be on my right. If you're really struggling with this, I would strongly encourage you to pull out your model kit, build the model as it is, and then look down the bonds to hopefully help you with this. The back carbon, of course, even though it's not shown, has a hydrogen and a hydrogen, and then it has a methyl down. So the methyl would be down, and then we have 2 hydrogens. There are numerous conformations that could exist for ethane as you rotate one of the 2 bonds and hold the other one constant. However, there are only 2 that actually have names that we will encounter. One is a staggered conformation. And one of the things that's also used to talk about conformations is a dihedral angle. And typically, a dihedral angle would be an angle between 2 planes. And in this particular case, it's going to be an angle defined between kind of the 2 bonds, or even also between these 3 atoms. And in the staggered conformation, the dihedral angle will be 60 degrees. In the eclipsed conformation, it will have a 0 dihedral angle. And if you were to then draw these instead in a kind of the 3-dimensional drawing, this, of course, is going to be what you would view as the front carbon. So, if we were looking at this again, our eye is going down this way. So that's why I have that hydrogen up and in the plane. And hopefully you can see that that is staggered and it would be lower in energy. Whereas in the eclipsed conformation, the bonds are overlapping with each other, hence why the eclipse, like, a solar eclipse in which you have the moon eclipsing or going over on top of the sun, that's what sort of is where the name comes from for an eclipsed conformation of an alkane. And so if we consider the complete 360 rotation about a carbon-carbon bond, so let's say we start at this staggered conformation here, and as we had mentioned, it's lower. And notice that in this particular case, we are keeping the back carbon constant, and we're rotating the front carbon. And so we can see here that if we rotate this 60 degrees, we now go to an eclipsed conformation, which is higher in energy. We rotate it another 60 degrees, we go to a different staggered conformation, but it has the same energy as the first one. Then rotate it again, go to an eclipsed, etc. And we can see that the energy difference between these two is 12 kilojoules per mole. That difference in energy between the staggered and the eclipsed conformation is referred to as torsional strain, or strain associated with twisting or rotating around that bond. And as we said, for ethane, it's only a 12 kilojoules per mole difference between the two, but still that's enough that at room temperature, 99% of the ethane molecules will be in the staggered conformation because it is lower in energy. And we can see that this cost, this total cost, is due to the overlap or eclipsing of the two hydrogens with each other. And these are due to some electron repulsion. And it's a phenomenon referred to as sterics, in which you have that sterics where these two are overlapping each other. In addition to the sterics making the eclipsed conformation higher in energy, one of the other things is that there's a phenomenon called hyperconjugation that also accounts for the lowering in energy of the staggered conformation. So if we were to look at the staggered conformation and realize, of course, both of the carbons are going to have bonding and anti-bonding molecular orbitals, but in this diagram we're just showing the bonding one on one carbon and the anti-bonding on the other carbon. And the same thing would happen vice versa, where you would have an anti-bonding on the other. The bonding is going to be occupied, the anti-bonding is going to be unoccupied, and you're going to have some overlap of the electrons similar to resonance stabilization. So this phenomenon is similar to the idea of resonance, in which you delocalize the electron density and help to stabilize a conformation. And we can see that you have this zone in which you can have that favorable overlap between the bonding and the anti-bonding molecular orbital. However, if we look at the eclipsed conformation, this is not favorable, and there is not that favorable overlap between the sigma and the sigma star orbitals on adjacent carbons, and that's also going to contribute to the fact that the eclipsed conformation is higher in energy or less favorable. So if we were to add another carbon and start looking at propane, and in this particular case, we're looking down carbon 2 to carbon 3 on the structure, we can see that we would have staggered and eclipsed conformations of the propane. And the difference in the energy between these two forms is 14 kilojoules per mole, and that additional difference is because of the fact that you will have greater sterics when you have an overlap of a methyl with a hydrogen instead of just a hydrogen with a hydrogen. So this is going to have greater sterics, and hence the eclipsed conformation will be higher in energy. Adding more complexity to adding butane, and here we're looking down carbon 2 to carbon 3 again. We actually are going to have several different staggered conformations. And so we can have the one named one, which we'll go through these also on the next slide, but this is going to be referred to as anti, kind of opposite, that those two methyl groups are opposite of each other. And you will hopefully see between this and on the next slide why that is the lowest energy conformation. Then we have our eclipsed, which will be higher in energy. And you can then, so we go to one eclipsed here where we have a methyl eclipsed with a hydrogen and a methyl eclipsed with a hydrogen. Then we go to the next conformation, which is slightly higher in energy than the anti, and that is because of another type of interaction, which is referred to as a gauche interaction. And that is meaning kind of adjacent to each other. And so these two methyls are large enough now that if they are that close to each other, they can cause a gauche interaction. Then we would go to a higher in energy eclipsed, because now we're eclipsing two methyls instead of just methyls and hydrogens. And so we have two methyls eclipsed, which would raise its energy more. Go back to another gauche interaction, then another eclipsed that does not have the methyls eclipsed, so it's slightly less in energy, and then finally back to the anti-conformation. And we can see the relative differences in these interactions because you can hopefully see from this slide there are some sterics. The anti-conformation has less steric hindrance because you've put those methyl groups opposite. They're farthest apart from each other. But when you start having the gauche interactions, you can hopefully see that there is some sterics there. Now, if we go to the anti-conformation, if you were to build a model and hold it such that it's in the anti-conformation and then rotate it around, it actually looks like this in terms of its three-dimensional shape. That's why when we draw bond line formulas for alkanes, we tend to draw them with this zigzag conformation because that's their lowest energy conformation. And so again, we can see these differences in energy, and we could use that information to calculate what an eclipse of two methyls is. You know, what is that energy cost involved in that? So if we look at this, we know that a hydrogen, each of those is 4 kilojoules. We know the total difference from that conformational analysis was 19. Subtract the 8, so therefore we know if we have a eclipsing or torsional interaction of two methyl groups, it's going to be 11 kilojoules per mole of energy. And so finally, you can have these tables that will tell you the different types of strain that occur in the molecules, in which whether it's torsional strain or torsional and steric hindrance, because as the molecules become bigger, that's larger amounts of sterics. And you do need to commit these values to memory so that you can complete a conformational analysis of a compound. So we're going to do a conformational analysis for 3-methylhexane looking down the carbon 3, carbon 4 bond. And so you first want to draw the structure and of course know kind of which bond you are looking down. And so in our first one, carbon 3 is the front carbon. It has a hydrogen, a methyl, and an ethyl on it. And for the most part, you're going to treat ethyl groups as if they were methyl groups in terms of looking at those overlap values, because they can also kind of turn. So it's really just the one CH2 group that would be in close proximity. Then our back carbon has a methyl and 2 hydrogens on it. So this would be one of our conformations. And this conformation has 2 gauche interactions. And recall that a gauche interaction, that steric hindrance there is about 3.8 kilojoules per mole. And so this particular conformation would have a total approximate energy of 7.6 kilojoules per mole. Then we could rotate 60 degrees, and I tend to rotate my back carbon, but if you prefer to rotate your front carbon, that is perfectly fine. It's just kind of a personal preference. Either way is acceptable. So you know that we're going to go from a staggered to an eclipsed. So now I have this methyl group eclipsed with the ethyl, a hydrogen eclipsed with that, and a hydrogen eclipsed with that. We know that a methyl hydrogen eclipse is about 6 kilojoules per mole. The 2 groups that we're going to call like the 2 methyl groups almost are like 11. And then the 2 hydrogens are 4. And so recall, of course, that this then will be summed up. So we're looking at 21 kilojoules per mole. Rotate another 60 degrees, and we would go to another staggered conformation. And in this particular case, we just have one gauche interaction of 3.8 kilojoules per mole. So this overall is 3.8 kilojoules per mole. Rotate again to another staggered. To another eclipse, not staggered, sorry. And so this methyl is 6 kilojoules per mole. This one is also, and so is this one. And so that gives us a grand total of 18 kilojoules per mole. Rotate another 60 degrees. We're going to go to another staggered conformation with just one gauche interaction. Rotate another 60 degrees to another eclipsed, in which we eclipse the 2 methyls together, which is about 11 kilojoules per mole. This is about 6, and the 2 hydrogens are 4, giving us again 21 kilojoules per mole. Rotate another 60 and we're back to where we had started. Now when I draw next we're going to draw obviously the energy diagram, and I tend to want to start with one of the lowest energy states. So I'm going to go ahead and call this my conformer 1 because it's one of the 2 that is lowest energy. Then this will be conformer 2, 3, 4, 5, and then finally 6. Now that we have completed what each of the conformers would look like, we could sketch out the diagram. And whenever you do a diagram, you want to label all of your axes, and then you're either going to want to redraw the conformers or use those Roman numerals to label them, much like I showed you how to do that just a moment ago, where I identified which ones were each. So we're going to talk about our relative energies in terms of kilojoules per mole, and recall that those ranged anywhere from about almost 4 to 21. So, and again, label your axes. It's extremely important that you have labeled axes. And then we're going to have rotation about the carbon-3, carbon-4 bond, and that's every 60 degrees. So 0, 60, 120, 180, 240, 300, 360. And so as I said, we're going to start the number Roman numeral 1, and recall that its energy was about 3.8, so that's going to be there. Then if you go back and look at your the notes from the previous slide, you will know that we then go to compound 2 that has a relative energy of 18. And that's going to be eclipsed, which is going to be higher in energy. Then we went to 3, which is also at that 3.8. Then we went to 4, which has 21. And then 5 was at an energy state of about 7.6. And then finally 6 was also at an energy of about 21. And then finally back to 1.